Hey guys, welcome back. So we're going to set up for experiment 2, which is the buffers experiment. I'm going to go ahead and set up my screen so that we can do that. Screen 2, I will share this. Get this out of the way, and then I will come into myself as the instructor. Get into our one-on-one class, and then set up my student view. And that way we're all looking at the same thing. Also go ahead and open my OneNote notebook because that's where I store all of my stuff when I'm doing this. And we'll go ahead and open an Excel spreadsheet just so that I can do my calculations because it makes it easier for me when I do. So I'll minimize that. And what I'm going to do is go into the second virtual lab here, which is the buffers. And I'm going to open this. And I'm going to go ahead and start. Now, this is about buffers. We've only recently started talking about the buffers. But again, a buffer is a solution that resists changes in pH when small amounts of strong acid or strong base are added. It doesn't really matter if it's strong acid or strong base, or if it's a weak acid or weak base. A good buffer is composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffer capacity is the maximum amount of a strong acid or strong base that can be added to that buffered solution before the pH of the solution changes significantly. Buffer capacity will be exceeding a large amount, when a large change in pH is observed upon addition of a small amount of strong acid or strong base. The larger the buffer capacity, the better the buffer. In this experiment, we'll identify the best buffer by comparing the buffer capacities. You'll add strong acid or strong base to water, aqueous sodium chloride, and an acetic acid acetate mixture while measuring changes in pH. You'll prepare 3 acetic acid acetate buffer solutions and add strong acid or strong base to each buffer to identify changes in pH. In the pH data, you will be able to determine which buffer has the highest buffer capacity. The acid dissociation constant, Ka, acetic acid is 1.75 times 10 minus 5. And there it is. I yawn again because I'm on camera. And of course, acetic acid CH3COOH plus H2O gives me H3O plus CH3COO minus. Ka of H3O plus times CH3COO minus over CH3COOH. My pKa is the negative log of the Ka. And of course, my Henderson-Hasselbalch equation, pH equals pKa plus the log of the conjugate base, here the CH3COO minus, over the acid, which is the CH3COOH. Okay. So that's all my background information that I need for this. Now I can go into my laboratory simulation. Calculate the pH of a solution prepared by dissolving 1.9 grams of sodium acetate in 67.5 milliliters of 0.15 molar acetic acid. Assume the volume change upon dissolving sodium acetate is negligible. Ka of CH3COOH is 1.75 times 10 minus 5. Okay. Now I'm going to pull this over here, and I'm actually going to use this because I don't want that. So I'm going to pull this over here so I can look at my spreadsheet as well. So I have this. And what it's told me is that I have 67.5 milliliters of solution. I also have 1.90 grams of that sodium acetate, NaCH3COO, and this is H2O. And of course, I have 0.15 molar CH3COOH, and of course my Henderson-Hasselbalch equation, pH equals pKa plus log of base concentration CH3s. CH3COH divided by the acid concentration. And of course, I can, if I make this wider, subscript there, superscript there, subscript there. And that'll make that look pretty like I want it to. I can go through and do that for anything I want to. And of course, I've just added those to my toolbars to make my life easier. I didn't want to do that for the whole thing. Just wanted to do two. I only do that for aesthetic reasons. It's not necessary for me to do it. It's just something I do for my own purposes. Now, I know that this is in grams. I know that this is in milliliters. So I often move these over here. I know that this is 0.15. This is the molarity of that. This is grams. This is milliliters. And so I know that I can convert this to moles by dividing by the molecular weight. I can calculate the molecular weight of this thing by using those molecular weights either from Alex or from my molecular weight table. But it's going to be better if I use the molecular weights from Alex. Now, I happen to have a spreadsheet that I have put together. Called Alex Molecular Weights. And the reason that I did this is because I wanted to make sure that I had all of the weights that Alex uses. So these are the Alex molecular weights, and these are the periodic table molecular weights. And you do this so that I can work with the numbers that it's got stored. These are the ones that I use for that to generate the table that are in the exam handouts. And so if I wanted to calculate the molecular weight for the NaCH3COO, I can do the Na, which is that Na right there, plus 2 times the carbon plus 3 times the hydrogen plus 2 times the oxygen. And then it gives me this number right here. Okay. So if I want to calculate the molecular weight for that, that gives me the number of grams per, sorry. So if I take the grams divided by the grams per mole, that tells me how many moles I have. Okay. So this is how many moles. Move this over. So this is moles. And if I wanted molarity, then I need to take this number right here and divide it by the volume in liters. I'm going to put that right there. So that's equal to this number divided by 1,000. So I take this number in milliliters, I divide it by 1,000, that gives me the number in liters. So I take the number of moles divided by the liters, and it gives me. So that's my molarity. So that's the molarity, moles per liter, for that, the base component. Okay. So if I want to put this into the Henderson-Hasselbalch equation, so I will know what the pH is, I need the pKa. So my Ka is 1.75 e to the negative fifth, because that's the value that they gave me. So I just put that in there. My pKa equals the negative that lovely value, which is this number right here. And so my pH is equal to the pKa, which is this, plus the log of the base component, which is this number right here, divided by the acid component, which is this number right here. And that gives me 5.11. Now, to 2 sig figs, if I'm not mistaken, 6. Let's see if it complains about that. And of course, it's going to complain about that because it doesn't do it right. So 5.12 is what it wants, even though that is not technically correct. That's okay. Use clean graduated cylinder to add approximately 50 milliliters water to beaker 1 and to beaker 4. So I need to show my labels. Where my DI water is. Here's my DI water. Add this here. That is 45, 46, 47, 48. This one's 50. Being graduated cylinder and approximately 15 milliliters of sodium chloride. This one. Here 2. It's 50. Sodium acetate directly to those. A cylinder, add approximately 50 milliliters of 0.1 acetic acid. I've got 48 here. It's 23. Nine. And of course, it only wanted one. Now we're going to 6 there. And then we'll go to phase the next phase. Add stir bar to the beaker. Put in the stir plate. Turn on the stir plate. Position the pH probe into there. Record initial pH. One, two. 1, 2. Using dropper, add 1 milliliter of 1 molar hydrochloric acid. So I think that the best buffer is the acetic acid sodium acetate solution because it resisted changes in pH up until we hit about the 5 mil mark. And then we hit this, place where we stopped resisting change. So writing is where we ran into that issue. So right there. Now we're going to do the same thing here. We're here. Here. This in here. 7, 1, 2. And we're going to add sodium hydroxide. So we're going to show our labels again. 2, 5, 6, 7, 8, and 10. Put this back. Take this out. This here. Clean that off. Take this off of here. Next one. Don't forget to record our initial pH. Initial pH here is 6.92. Do it again. 2, 3, 6, 7, 8, 9, 10, 11, and 12. Oops. Oh yeah, too much. Oops. Only 10, not 12. Off. Take this off. Stir bar into here, to there. Data. Initial pH is 5.36. A little bit lower than it was before. So sodium hydroxide hasn't changed nearly as much. 1, 2, 3, 4, 6, 7, and 10. Back, taking this out, and then cleaning that off. And then putting this over here. To the next. Yes, I'm going to the next phase. So again, plotting this volume of stuff that added, pH is the dependent variable. Again, line graph creating that. And again, the thing that is least changed is that acetic acid. So try to save this. Sodium acetate. So now I can say, go on. Yay. Which of the following additions will exceed the buffer capacity? Buffer that contains 0.2 moles of acetic acid and 0.1 mole sodium acetate, total volume of 2 liters. 2 moles of acetic acid, 1 mole of sodium acetate. So I have less buffering with the sodium acetate than I do with the acetic acid. So it's going to be an addition of sorry. So I can add more base than I can acid. Looking at the base size, I need to be looking at the acid sides. And so the 100 milliliters of the 0.15 is probably going to be the one that's the problem. I'm going to guess that. And hooray, look, that was the problem. So go on. Add approximately 0.5 grams of sodium acetate directly to beaker 1 and beaker 4. So this one in here, I'm going to tear that. 5 grams of sodium acetate. It's 0.52. Tear that again. 0.57. Or so. Yes. Okay. That down. This one. 10%. And approximately 1 acetic acid. $47. Again. Tear that. 0.73. Zero point 0.75. So 2. $73. Come on, Montana. Six. Sure. Mhm. It's 99. Sometimes it sticks while I'm trying to do this. I hate it. Stir there. No, something updated to 5.3. Which one am I supposed to add? Chloric. This up. 1, 2, 4, 5, 6, 7, 8, 9, 10, down, it's out. Wait, it's off. Here too. Pick up bigger too. Yeah, we need this. Damn it. Let's screw that. 5.3. 2, 6, 7, 8, 9. Yeah, one of the things I really hate about this is that it's very unrealistic because in the lab you'd actually have to write down each one of these things. So I find it unrealistic that they make you write down one of them, only the one. And then they imply that the rest of them are not important. It's just very unrealistic. It's not really how this works. You have to stand there and write down all of it. 5.35. And granted, it can be that quick because you can have somebody else write down everything. So I go this, and then somebody else writes down 5.24, 5.13, 5.02, 4.90, 4.76, 4.60, 4.38, 4.03, 1.20, 1.18, and they'll tell you when to stop. That kind of stuff can happen. But it's very unrealistic to imply that doesn't happen. It's more realistic to me to have this compare, to have you say, okay, 5.33, and you have to move this, like this up. 0.25, 5.17, 5.9, 5.00, 4.1, 81, 70, 8, 4.4, 4. And then you know that you're done, and then you can pick this up. That way you're sort of tracking it in the same kind of way that you would be in the lab. But I know that most students don't do that. So anyway, stop yakking about what is more realistic. So pull this back off of here, and we can go to the next phase. Hooray! And of course, HCl, pH, to creating that, we're saving that, and now we are looking at what is it that changed, and which one is the one that changed the least, and that is that solution 3. So solution 3 is the one that is the best buffer. So the highest buffer capacity is solution 3. Awesome. And I see that again because it has the least change in pH. So that's solution 3. Awesome. Close this. Did save this, so now I can go to the next phase. And I would expect the same behavior. My server. So here, the probe. New extra. Must have annoying sound. Then we put that in there. 5.34. 4. And we're going to get the sodium hydroxide. Right. Pre-record. Start big pro 5.35. 135. Almost down. 2. 6. 7. 8. It's back. Take this out. Take this down. Up. This is the next one. Up. Here. 5, 4. 1, 2. 6, 7, 8, and 10. Back. Out. Take this to clean it. Find this down. Closing this up. Taking this off. And going to the next phase. Making yet another graph. Age second. Saving that to update it to say that change the least was that solution 6. So this one changed, this one changed, this one barely changed. So solution 6. Hooray! And that was all of what I had to do. Awesome. So going back into data, I want to go back. I do not see anything down the bottom that says calculate yada yada yada. So I don't see anything that I need to look at here. Now, the only other thing beyond this that I saw at all were these graphs. And these I have in my data. So all of my data is here. So I'm good. So I have my data here. I don't have anything else here. I mean, I can go back. to the introduction. If I wanted to add this to PDF, I can. If I wanted to screenshot this, I could. And sometimes I do this as well. Just to make sure I have everything. It depends on how comfortable I am with that material, whether I will do that. It's in there, so I can now close this out. This out. Because I did that calculation. If I needed to look at that calculation again, I could always save that. That's the one other thing that I might want to be looking at is that I do that particular calculation. So I want to come in here. And look at how I did this. So I can look at this, say 1.9 2 wait. Let's see. Well, that result divided 0.1 second term. First term. 1.75. Negative. H. 1.6341. And again, that should be all the explanation I need to be able to replicate the calculation that was done. I have the question, and I have the answer that I entered, and this explains to me how I did that calculation. So here's the Excel spreadsheet that I sent it. Here's how I did this calculation. And here's the answer that we entered. So that tells me everything about how I did this calculation right here. So that should be everything that I need. I'm happy with that. Hopefully that was cool for you. I mean, this I don't think was terrible. So hopefully that takes care of everything. And if you have any questions, comments, problems, please let me know. I will get this loaded as soon as I can. And I will talk to you guys soon. All right. I will talk to you later. Thanks, guys.